further ado, John Greenlees will speak to us about algebraic models for rational t-spectra.
Thank you very much. Of course, but before, Paul's messed up my the start of the category, because my job on this last, just before this last talk, is for us to thank all the organisers, Paul and Catherine and Bjorn and Dan. Very good. Now, I think Paul got my title slightly wrong. I think he said algebraic models of rational G spectra, and well, we've just got a special group today, the circle group. And I just wanted to notice that this is not a finite group. I mean, there haven't been so many, but of course, JD's talk this morning had some excellent non-finite groups. But I mean, the circle group needs more attention. Anyway, I'm going to give it some attention today. And of course, this is the same as SO2 or U1 or whatever you like. But so it has featured, for example, in Dave's talk, and I'll mention something about that in a moment. So that was the first part, algebraic models of rational t-spectra. Well, I mean, one of the things that first of all, this talk isn't about finite groups. Secondly, it isn't about difficult calculations. It's actually a little bit of an almost algebraic segment of stable homotopy category. So I'm really doing algebra, but there we go. And the word rational, I may forget after a while to say things are rational, but there's a sort of global tensoring with Q going on. So this is just to prepare everyone. Then there was the subtitle. Of course, there's been an algebraic model known for rational t-spectra themselves for some time. I'll try and work out the time in a moment. But this is really, the talk today is really about a multiplicative case. It's about having algebraic models for E infinity ring spectra of various sorts. So I've got this times sub 1, meaning naive commutative or non-equivariantly E infinity, or the least commutative of the N infinity operands. So that's what that means. And this cross sub T, that's the most equivariant one. So E infinity T, or whatever you like, or fully commutative, or the commutative rings in orthogonal spectra, or whatever it is. So that's just the title. And then the talk today is really about the following theorem, which has been proved by myself and Magdalena. Which says that there is an algebraic model for equivariantly commutative rational t-spectra. So I'm going to write it this way. So C sub t, C for commutative t because it's equivariant, algebras in t-spectra. And just for now, I'll mention the rationals. And it's going to be, well, commutative algebras in some other category, differential graded objects in some, this is an abelian category. I mean, that's one of the things that, this isn't an abstract equivalence. This is an equivalence which lets you do calculations. So I've got to convince you that this category is small and calculable. And of course, Dave made a good start. If I covered up normed, he managed to give the definition in one breath. So, in case any of you didn't catch it, I will tell you a bit more slowly. And indeed, I'll try and build up to this as we go along. Okay. So then there's the context. So let's just, and this is supposed to make sense for any compactly grouped G, and I'm just going to tell you the situation just so it puts it in context. So for rational G spectra themselves, the idea is that they should be differential graded objects in some category A of G, and I'll tell you which groups, the status in a moment. Or we might have C1 alg G spectra rational, and these will be C alg DG A of G. So the same A of G in this case. So there's not a great deal of change. And then there's CT alg of rational G spectra is commutative algebras and these norm things. So these are conjectures. I mean, they're not known in general, but let's see what is known. So in the first case, when do we have an algebraic model? So we have it certainly for finite case. We certainly have a model, and well, first of all, there was essentially the answer was given by myself and Peter May in the appendix of the Tate volume, but that wasn't even a proper model category equivalence. I suppose we need to go on for Schrader Shipley to do a Morita theory proof, and they go on with Dave and Magdalena refining it further into better, more monoidal versions. Then it was known for tori by myself and Brooke Shipley, well, eventually appeared in 2018. And then, well, there's also for rank 1 groups, all of them connected or not, and subgroups of SU3. Well, I'll come back. I alluded in my abstract to the fact it was an antidote to my talk about SU3. So the title of my talk for SU3 was Rational SU3 Spectra in 18 Blocks. And the point is that there were 18 separate special cases to talk about, and I want to get away from the idea that this is a complicated thing with lots of epicycles. It's just something quite simple when the group is simple. Okay, then, well, for finite groups, if you had a model equivalence for finite groups, you can try and lift it to a equivalent equivalence. Model equivalence is equivalent equivalence. For not naive commutative, and I suppose this was Dave and Magdalena and I did that. And for the circle group, we did that one again. This is for the circle, T. And I suppose that if you did an infinity categorical version of these statements, it would actually be quite routine to lift it to an E-infinity version here. So I think you shouldn't think that this is a big step. However, it is a big step to go from the second line to the third line to actually do equivariantly commutative, because the category changes, roughly speaking. And in the case of finite groups, I first learned about this in the Galapagos in 2017 when Christian Wimmer gave a talk, and I must say I didn't believe it to begin with, but because it was amazingly simple answer. Wimmer, in his archive version, is in 2019, and then there's the circle group, which is what I'm going to talk about today. Okay. So I've been teasing you slightly about this A normed of T, so I think it's time to come clean. So A of G, it's supposed to be, the model takes a piece of data for each subgroup, each closed subgroup. So roughly speaking, everything is a sheaf over the category of conjugacy classes of closed subgroups. So that's why it gets complicated when the group gets bigger, because the understanding conjugacy classes of closed subgroups is big and complicated. However, it's very simple when G is the circle. So I think from now on, G will be the circle. I'll try and say T all the time. So subgroups of T up to conjugacy are the same as subgroups because it's an abelian group. And they are just the cyclic groups and whole group. And I'll call this lot F, and the other one will be called by its name. Okay, so the idea of the model is as a piece of data for each of the finite subgroups. It's the same data essentially, and then I've got to take that and, taking into account the fact that these groups converge to something, splice in this. So that's how it goes. So the slogan for the talk, if you like, is that all is F times co-free plus T. Okay. So the last thing I wanted to do was tell you what the category is for A of T. It looks like this. So A of T. So I have one piece of data for each finite group, and it's a module over the polynomial ring on one generator of degree -2, which is a cohomology of BT. And actually, I want to just, it's the same thing for all of them, so I just want to take a product of copies of that, one for each finite subgroup, and then I get a module over that. So this is a module over this product of copies of C, which is going to be called OF. So that's a pretty horrible ring, but they'll get constraints. And you should think of the model as consisting of n together with a little bit of extra data about it. So the extra data says that when I invert Euler classes, which I have to tell you about, but when I invert Euler classes, it takes a special form. Like this. So in other words, you should think about this as saying, I take n, imagine there's only one factor of C. So I take n, I invert C, I get a module over Q of C and C inverse. I choose a dimension in which to generate it, because it's two periodic, I could choose any one, but I choose this one. You should be thinking about the localization theorem yeah. Very good. And then I want to put a dot here to remind me that this is obtained by extension of scalars, and a dot here to tell me that was obtained by inverting Euler classes. So the only thing I haven't told you is what E was. So E is the multiplicatively closed set generated by functions C to the V, where V was a function from F to the natural numbers, which is 0 almost everywhere. So this E inverse OF thing, which maybe we can step in here, E inverse OF. I've given you a definition of it now, but if you prefer, you can think of it as the restricted product of the Lorentz rings. So it's adelic. Okay, so then the exercise for those of you who are bored is to calculate the stable homotopy groups of spheres from this. Rational. Oh, I'm not joking. Yeah. Well, not really. So I have to tell you what is S0 in this algebraic model. It is the object consisting of OF, E inverse OF, tensor Q in degree 0, Q here, and the exercise is to calculate what self-maps of the sphere are. I suppose we're thinking of the derived category of A of T. I mean, the differential graded. and I want it in all degrees. And so this involves an exercise. It involves you working out that A of t has got injective dimension 1, identifying the injectives, writing out a resolution, and doing a calculation. But it is something that if you didn't pay attention to the rest, you could do in the time available, or less. Okay. Okay, so that, now everyone's got an exercise. Where was the... Oh, here we are. This equation all is f tensor co-free plus t. So I've got to first of all tell you about finite groups, then tell you about co-free, and then tell you about splicing. That's the plan for the rest of the talk. Okay, finite groups. So for this section, G will be finite. So what was how do we do this? What was G spectra? I'll do it at the top here. G spectra, rational G spectra. I'm going to stop saying rational, but it is rational. And so we know what the answer is. They're differential graded Mackey functors, or chain complexes of Mackey functors. And the original proof said, well, G spectra, there's a Postnikov tower for G spectra. The little calculation shows you all the K invariants are 0, so it splits. That's the proof. But let's think about an alternative. I can remember what a G Mackey functor is. It's a functor from the stable orbit category in degree 0 into rational vector spaces. Okay, and once I've remembered that, well, I also noticed that what are the stable orbit? They're things like G mod H plus, and then the maps between these things, G mod H plus, G mod K plus. This is entirely in degree 0 because G is finite. So this is functors stable orbit category into Q mod. And I suppose really Morita theory will tell you that because G spectra is generated by these small objects, G spectra is equivalent to that. So we could do it that way, or we could remember, or we could say, what are G spectra anyway? Perhaps they're spectral Mackey functors. So then I'd have functors from the stable orbit category into spectra. And because spectra are the same as graded rational vector spaces, I've got an equivalence here. Okay, so roughly speaking, that's a way of having a proof. But this doesn't really, it's already been, Dave alluded to the fact that this doesn't explain what Mackey functors are. So I'm going to take the stable orbit category and remember that these objects, G mod H plus, actually they're rather complicated. You can break them up into pieces. There's a sum and, which I'll just call sigma H, which other stuff. So it's just as well generated from the sigma H's instead. And the point about the sigma H's is that their endomorphisms of sigma H is just the Weyl group WGH. And there are no maps from a sigma H to a sigma K if H isn't conjugate to K. Of course, this is the same as functors from orb G into Q. So that, I've again used the fact that we're over the rationals in those two places. And if we said that, then of course I get a similar thing for orb in degree 0. And then, orb G and isomorphisms. So no maps between sigma H and sigma K if H is not conjugate to K. So therefore, this whole thing is just equivalent to a product of the conjugacy classes H or QWGH ones. And so I probably just ought to show you just, since this is the single most common misunderstanding, I think, of these rational models, I just remind you, if G is the group of order P, what's a Mackey functor look like? It's got a value on G mod G, G mod 1. So I think this has been said quite often already, a restriction and a transfer. But the point is that rationally, this is a sum. So I can take M of G mod 1, and I can look at the fixed point Mackey functor. We saw the fixed point Tambara functor, but the fixed point in Scott's talk, I think, but the fixed point Mackey functor is much simpler. It's just like this. And then that's a summand. And what's the other summand? Well, I don't need anything more at G mod 1. I have 0 here, and I have something else which I'll call B of G here. There's only one possible choice for that. And so the whole thing, the M, the whole Mackey functor, is captured by this piece, which I'm going to call V of 1, and this point, this which is V of G, and they're unrelated. So so an M lives in here, and a V lives in here. Okay, so that's all well-known stuff. So how about the multiplicative situation? We've got G spectra here. Rational, of course, and this is equivalent to functors from orb G cross Q mod. That's equivalence. I've sort of sketched that. But I might want to look at E infinity algebras in here, E infinity 1. 1 is the trivial group. There's a forgetful map and a free map on the left. This is a monadic adjunction, and because there's a nice E infinity operad which works in rational vector spaces as well, it's not hard to do the same thing on the other side. And that's also monadic, and you can, well, it's going to be a zigzag, but you can get from this side to that side, and because the free functors are well behaved, when you forget them downwards, if you do it on something cofibrant, you forget down on something cofibrant, it's cofibrant. That shows that this is an equivalence. That's how we prove that. And of course, I should point out that the thing on the right-hand side, we could just rewrite this a little bit, because in commutative algebra, E infinity algebras are the same. Can be rigidified to commutative differential gradient algebras, so this functors from orb G cross into commutative algebras over Q. Okay, well, now we can go further. We can think about algebras over E infinity G. And again, it's got, well, I suppose from the bottom, but it's also got one here. So it's got a free functor, and this is also monadic. However, it's not so clear what to do at the other end, because we know what I ought to be writing here, or at least I've told you it should be. This should be maps from the orbit category. I didn't tell you, but now I'm telling you. So this is Wimmer's result, that actually I look at all maps into commutative algebras from the orbit category, so including the projections. They also induce maps in a covariant direction on the rings. So you might be surprised, if you're used to the fact that norms are multiplicative, but they're not ring maps, you might, that might be a bit confusing, and that's why I didn't believe things, Wimmer's result initially, but the point is, I'm not talking about M's, I'm talking about V's. So on V's, they're maps of rings. So then, there's an obvious map downwards. There's some sort of general categorical Klein extension going upwards. And what Wimmer did was he showed that this functor was well behaved, and using geometric fixed points, you could construct a map, an infinity categorical map here, and that it behaved very well on free objects, and therefore that's enough to show an equivalence. So this is Wimmer's 2019. So that is, so you know, this says this is this category, or the abelian category corresponding to that, diagrams of rings based on the orbit category. That's the model. Okay. So the brave people say, ask for any questions at this point. We just dealt with finite groups. So in terms of this equation, we've done F. Now the next bit is to do the co-free thing. So any good life coach will tell you that there are three choices which determine your destiny and success. So this is about the three choices. And they're really choices about, well, the first choice asks what it is about. So the first choice is, do we talk about free spectra or co-free? So I've already asked this. So this is free T spectra. Well, of course, they're equivalent. I mean, what is a free T spectrum? It's a thing like ET plus smash X. Or co-free T spectra. What's that? It's a thing like function spectrum of maps from ET plus into X. So those are equivalent, and I've just given the game away by mentioning these facts. And you should probably think of this one as cellularization with respect to right Bousfield localization with respect to T plus. And this is left Bousfield localization with respect to T plus. Okay. So, but then there's also, we might do the same thing in algebra. We might look at modules over this ring Q of C that we've already seen. It's torsion modules, so that means C power torsion modules, QC modules. Versus complete QC modules. And I'm not going to write this down, but if you wanted to think about abelian groups and P, you'd have P torsion abelian groups and P complete abelian groups. Okay, so that's the first choice, and we choose co-free. Because it's much better behaved in terms of monoidal structures. It's got some disadvantages too, but I hope not to have to mention those. Okay. Second choice. Well, this is a little... now we know we're talking about co-free T spectra. What is that? I've just told you it's the left Bousfield localization of something. So I'm going to write, because it's this, I'm going to write it lambda 1. So 1 is for the trivial subgroup, which is the co-isotropy in this case, of T spectra, but T spectra are just S modules in T spectra. So that's not much choice, but there's something better you could do. You could look at the left bias field localization of S0, which is otherwise known as DET+. I just told you how to complete something, really. Modules. And because the map from S0 to DET+ was a non-equivariant equivalence, and I've just completed, this is an equivalence. Okay, I'll explain why that's better in a moment, but let's just do it for QC modules. For QC modules, there's no real difference, because QC is already complete. It's a graded ring, so it's already complete. I'm sorry?
What do you mean with D?
Right, I mean dx is function spectrum of maps into S0, so DET+.
Yeah.
So it's the, and the map from X to this is the left bias field localization. Very good. So, but if I was doing this in Q modules, because it's a graded ring, there's no difference. There's no difference here. But in abelian groups, the thing I'm not writing down, it would be a question of whether I was thinking about p-complete abelian groups or p-complete modules over the p-adic integers. That's a good thing to think about because there's a well-known module over the p-adic integers which is going to get killed off, p-adic rationals. So, yeah, very good. So now I can tell you why I want to think about this second thing, not the first thing. It's because actually this ring is very special. It's formal in a strong sense. So firstly, I can take fixed points. So this is in T spectra. I can take fixed points, dBt plus, in spectra. I can then use Brooks-Shipley's algebraicization result, which says this is the same as modules over the cochains on Bt in rational vector spaces. And then you could do that in the commutative sense because we're working over the rationals. And of course, we know what the cohomology of Bt is. It's a polynomial ring on one generator. So that's formal automatically. So of course, this is the uncompleted thing, but it's already got an algebraic model. If I complete it, then I can complete this to getting complete QC modules. Okay, so that's the second choice. I want to characterize this as categorical. That was the completion operation versus module theoretic. And I choose modules. Okay, so that's the second choice. And then there's the third choice, which is which side of the causal fence do you live? This is a causal choice. So roughly speaking, you should be thinking about the fact that on the one side you have cochains on something like Bt, say, which is commutative but big, versus its causal dual, which would be chains on the loops of Bt, which would be chains on T, which is small and, well, in principle it's non-commutative. In this case it probably is commutative, but in general it's non-commutative. So this would be like saying lambda 1 DET plus modules is equivalent to, well, C star T modules. So notice, I mean, there's no, this is all modules, this is complete modules. So, I mean, I mean, we shouldn't worry about the commutativity since they're both commutative, but C star T has got infinite homological dimension. Thinking into Dave's talk. So whereas homology Q of C has got finite homological dimension 1. And then there's the same thing happening. Oh, and then I should probably rephrase this as saying this is like functors from the topological category with one object and endomorphisms T into Q mod. Because that's the thing that's going to come up. Whereas in the QC picture, we've got QC modules completed being the same as modules over the exterior algebra on a single generator of degree 1. Okay.
When you said C completed, are you completing Q of C or are you completing the category?
I'm completing.
And
that's also
box around module.
I'm sorry?
There's a box to the word module here, so it seems like we were.
Oh, right, yeah, but you're quite right. I mean the category of modules rather than the category which is formally obtained by localization. So, thank you. Okay, and on that's the choice on this side. So the whole thing to take away is that we've got lots of models. We've got co-free T spectra. We've got functors from dot into well, Q mod perhaps, and we've got complete modules QC. I thought there was another one I wanted to write down there. Apparently not. Okay. So that's the takeaway. So even though we've made these three choices and guaranteed our successful destiny, we probably need to occasionally backtrack and take the advantage of the other routes. Okay. So now we've done the F and the co-free, we've got to do the multiplication of the two. So really we're going to, now we're looking at F co-free T spectra. That is to say ones which are, these are the ones which are of the form EF plus. This is EF plus, the universal space for F spaces. F is still what it was before, the finite subgroups. So this is supposed to be the same as functors from orb F, or maybe I should say stable categories from orb F into Q mod as before, and I'm going to do this same trick picking out just the isomorphisms and getting the orb F to Q mod, but with a cross. So now we've got we've got this category. Where's it going to go? We've got this category. It's sort of got an object C1, object C2, object C3, and actually the endomorphisms of that'll be T mod C1, that's T mod C2, and then there'll be maps between them, passage to quotient. And then like this. And unfortunately that's a little bit of a complicated category, but we're going to simplify it. I could instead have taken the one which has got same objects, but now I have T everywhere, same thing. And these are just the identity. Yes, they do go there. And you can check that there's a map from the upper one to the lower one. So this is the category all. Yeah? And this is the category which we might call P cross T. There's a map like that. What is P? P is supposed to be just the thing. It's the division. So this is P. 1, 2, 3. Whoops. 1, 2, 3, 4. Etc. Okay, so we have there is a map, and it is an isomorphism, provided we map into the rationals. So, so carrying on from here, this is equivalent parameters from P across this thing into Q modules. And, well, we could just adjoint things over. This, and this we've already seen what this is. This is complete QC modules by the thing in the box over the side. So, in other words, this whole thing, every object of this, every object of this category is just given by, it's a diagram of complete QC modules indexed by the category P. So, hence, consider, well, it's category A, T, F, and its objects are N hat S. But they're supposed to be diagrams, so we've got there really N hat 1, N hat 2, N hat 3, etc. And that's what I've justified so far, but when we want to think of them later, what I'd like to think of them as just modules which are, let's just call them N hat. It's a product over all S of the N hat S's, but then I've somehow got to pick out these extra structure maps. These are what encodes the norms. And notice the norms, they still increase the subgroup, but they all go between QC modules. So these ones, so how do I encode that? One way to do it is this. I could take OF, which is this product QCs, and I could just remember the ones which are multiples of D. So, product SD QC. So really, that's an idempotent piece of OF. It's, if you like, there's an idempotent which is supported on multiples of D. And this is an isomorphism. I just take, the S factor to the SD factor, but then I could take N hat, and I could say, well, I want to map from N hat S to N hat SD. What do? I take ED star N hat, and then I pull it back along this isomorphism. And that's what I call these maps. These are the norm maps. This is norm 3. This is norm 2. This is norm 2. This is norm D goes like that. So I'm repackaging this as a normed OF module of a particular sort with norms which go n hat to ud star, ed star, n hat. And of course they're supposed to compose, right, so norm D, norm E is norm DE. Okay, so we didn't need to do that in this case, but we will need to do it later. So this is called a normed complete OF modules. Right.
John,
Hi.
on that board there, when you start with F copy T spectra,
I'm sorry, can't hear you.
on that board, when you start with F copy T spectra, would you like to add some more crosses to those categories?
Oh, yes, please. Now, where do I want?
The first bracket,
Not here. That's stable orbit category.
okay.
But here,
Yeah, and later, the P,
P. Oh, what am I doing? Very good.
that's a cross to that P. Maybe.
Yes, because I'm only telling you about FCO-free spectra. Thank you very much.
One upper as well. Just above. Yes.
Thank you. Right, I have got ahead of myself. So, this is ATF normed. What we showed over here was that FCO-free T spectra is equivalent to A hat F TF without the norms, and I now want to do what we did for finite groups in the case of the circle group, to exactly this step. So I have started with FCO-free spectra here and gone all the way up to E infinity G spectra, and used the same argument to replace orb F here, orb F cross here, to orb F here. And so I first of all defined the category, and now I suppose we should state the proposition, which is that
Which category do the little NDs, are they OF module maps? Or
they are OF, they're modules, they're maps of modules over the map from OF to ED star OF. Yeah, over new D. And each factor, I mean, in this case, I just need to say that each factor is a QC module map. And so then the statement, I think Magdalena has more or less saved the situation. The CT algebra map, CT algebra in FCO-free T spectra is the same as commutative algebras, C-alg in, well, normed DG, a normed, a hat normed TF. Right, so then you should be thinking about this and then adding norms between all the factors. Very good. So now we have to, fortunately the piece, so we've done the FCO-free piece, we've done F cross co-free. The T piece is easy. I don't know if it gets a separate section. Maybe it does, which is T spectra over T. I mean, that is to say the geometric isotropy is exactly T, the F contractible. And then, of course, it's well known that T spectra with geometric isotropy T exactly, F contractible, is T spectra over T. I can just take fixed points, either categorical or geometric, it's the same, and get an equivalence with spectra. And because we're rational, it's Q modules. And so this is classical. And then you can check that E infinity, that is C1 alg and CT alg, are the same for these two things. To get that CT alg of T spectra over T is C1 alg Q. Good, so it's just left to splice things together. Splicing. I think probably, given the time, I will state the splicing and then give you an example and then stop. So there's the theorem, which we've already stated, which was that there was T spectra. So I guess this is theorem with Rook. T spectra would be equivalent to modules. There'd be differential graded modules over AT. And I think I wanted to just tell you something about how you prove this. Which is like this. You could say that the sphere spectrum, you've got the Tate square, which is a homotopy pullback square of rings. So that tells you that the category of modules over S0, that is to say T spectra, is equivalent to a suitable construction on the objects here, here, and here. But what, and each of those is formal. So this gives S0 modules is equivalent to cellularization of modules over this part. Let's give it a name. Let's call it S0 cospan. And the point is, we did this thing for ET plus, DET plus. It was very formal. It was isotropically formal, and then so we moved to non-equivariant spectra, and then each of the rings in particular was formal. So that same thing happens here. So I just need to tell you what the homotopy is in this case, and it is just Q, homotopy of E tilde F, OF, which is the homotopy of this, and this is E inverse OF. So then it's not so surprising that this category consists of modules V, N, and E inverse OF to V, where these maps are like that. So this is what it is for A of T, and so then we're going to look at CT algebras in this case. So we have, maybe that's bad, CT algebras in T spectra, rational T spectra, is equivalent to commutative algebras in DG normed, A normed T. So the only thing I've got to tell you is what A normed is. So here, this is the category A of T. It's an N, which is a module over OF, a V, which is a rational vector space, and this thing. And A normed is exactly the same thing, but so A normed is the same thing, except that the thing in the box has to consist of two normed OF modules and a map of normed OF modules. So this is again V N inverse F tensor V, and this one, this is normed. So the fantasy proof is that you can take the same proof that you had in the white and convert it to yellow, but that doesn't work because we don't have a category of T spectra which looks like the additive thing, A normed of T. So maybe I can just say example. What is example? So the question is, which E infinity G T spectra do you know? Well, maybe the first you might think of is dy plus. So I take Y as a T space, Y is a finite T space. What object should it be in this A normed? It should be, well, in fact, in this case, N is actually a product. N is the product over S of REL cohomologies of the fixed points of Y. And then that maps to E inverse OF. That's a cohomology of Y fixed. I suppose these are, and cohomology. So that's supposed to make you think that this. Oh, and why is it normed? It's normed because of the localization theorem. So that's supposed to make you think that maybe you should have thought of the A normed of T as a reasonable model in the first place. So the actual proof that you give here has to go via a different method, by the categorical method, which wasn't guaranteed to make you successful and have a wonderful destiny, but nonetheless, that's the current proof. And I should stop early at this point. Thank you.
Are there questions? The obvious one is, what are the free algebras? You're going to tell me that's the obvious question and you don't want to answer this?
Well, I mean, I guess I've told you enough information to answer it yourself, but we have not done this exercise.
Okay. Anyone else?
You said the bottom right-hand corner is norm, so is the E inverse OF?
Oh, yeah, the norms are just given by the inclusions of the fixed points. So when I have them going from CS to CSD, I've got the CSD fixed points inside the CS fixed points. That induces a map in cohomology in the other direction. Yeah. Thank you.
Anyone else? Not? Let's thank John again.